1.4, functions. You've seen functions before. Can somebody tell me what a function is? What's your notion of a function? What's a function? Yeah.
Any operation you do to a certain number, like x, a certain set of numbers.
Okay. So you have a set of numbers, and then you do something to that set of numbers. Okay. That's you could think of it that way. Any other ideas of? You could say almost anything. Yeah, Victor.
Is it a set of coordinate values for which there's only one value y for every value x?
Okay, so you could say, maybe you've got a bunch of points on the plane, and to every x value there corresponds only one y value. Right, so that's sort of. Let me give a pretty general definition of what a function is. So the idea, you have two sets. So you have a set A, and you have a set B. Okay. And so a function is, so a function is something that, let's say, a rule, a construct or rule, which assigns to each element in the first set. Let's write it like this: a function f going from A to B. Function f going from set A to set B. So A and B are sets. Function going from A to B is a construct, a rule which assigns to each x in A an element f of x in B. Okay. So it takes something in the first set, right? It takes some x in the first set, and then gives you back something in the second set. Okay, and it does this in a consistent manner. Right? It doesn't change its mind about how this association goes. Right? If you give it this x, it's always going to give you that f of x. It won't say sometimes I'll give you f of x and sometimes I'll give you something else. Right? Okay. So basically, it's something that takes in something in A and returns something in B in a consistent manner, right? In a well-defined, let's just say, consistent manner. Right? It's not whimsical about it. Okay. So the notation is that we'll usually use is something like this. We'll write f goes from one set to some other set. I was writing A to B over there. Doesn't matter. Taking x to f of x. Right. So the way you read this in English is f is a function from what's called the domain D to the range R, assigning to each x and b and f of x in R. Yeah, Mariah.
Could you explain domain and range one more time?
Domain and range is just the function. The domain is the set that the function gets things from,
Okay.
and the range is the thing that the set that the function, the set where the functions, the set of things that the function spits out,
Okay.
it returns to you. Okay, so like this would be the domain, and this would be the range. right? So for example, you can have some function going from the class roster, so students in his class, going to a set of letters. Right? You have some function. At the end of the course, I'll create a function that does this. Right? Right, going from each student X, to the grade of student X. Right? So this would be assigning the grades at the end. If I have, if I write something like this, then what I mean is that you have a function going from the non-negative reals to the reals, right? It takes in a non-negative real number, returns you a real number, namely, it takes in some x, a non-negative x, and then returns you the square root of x. Okay, returns you the square root of x. And I should say that in this class, and typically, when we write the square root of x, we mean the positive square root. Okay. We're not going to take this to mean plus or minus the square root. If I wanted to talk about plus or minus the square root, I'll write plus or minus the positive square root. Okay. So all this is just describing the square root function. Okay. So this, for example, this is the square root function. And I should say that usually you can abbreviate. One often abbreviates this, for example, as so often you just write, instead of writing this full-blown thing here. So if you're in the back, you can't see. At the very bottom, I have this. So instead of writing this full-blown, detailed description, you just write this, and you assume that the domain is as large as possible. Okay, and assume the domain is as large as possible. Okay. So, you could take your square roots on a smaller domain, right? You could say, I'm only interested in the square root function for numbers bigger than 100, say, right? So that would if I wrote something like this, then that's a different domain than the other guy, right? So if I just write this, then there's some ambiguity, right? You don't know what the domain is. Whenever people write it like this, you just assume that the domain is as large as possible. In this case, the domain is going to be all non-negative numbers. Okay. So you lose something when you write the abbreviation, but you just, with this assumption, then you don't need to write it out. Anyway, that's just convention. Okay. Any questions so far? Any questions? Okay, let's go on. Okay. Let me make another comment. There are two terms that are often used sort of in similar senses, range and image. Okay. So let me make clear the distinction. The image of F is the collection, the set of all example, the image, so if we have f of x being the square root function, then the image of f is what? What comes out, what is the collection of all outputs of the square root function? What set is that? Victor?
0 to infinity.
0 to infinity, right? It'll be 0, 0 to infinity, right? Because these are, you can get all of these things, and you can't get anything else, right? At least not unless you start talking about complex numbers, and we're not going to. So, right, so the image of f is 0, infinity. But you notice that over here, I wrote the range is R. Okay. So the range isn't exactly the concept of image is something a little bit more precise. It says I'd like to know exactly what comes out of the function, and the range is just the set that the function maps into. Right? It doesn't have to be exactly the set of outputs, but it basically just has to contain the set of outputs. Okay. So the range is just range of f can be any, is basically any set containing the image. You don't have to be so precise about it, right? So I could say this function, right? I have a square root function. I have a square root function. It goes from the positive, the non-negative reals. Its domain is the non-negative reals, and then for the range, I could write 0, infinity. That's perfectly fine as the range, right? Because that's what the function maps into this set, right? I could also write the real numbers, right? Because certainly I get real numbers out of the square root function. I could write the complex numbers, right? Because my numbers are real, and the real numbers are contained in the complex numbers. Right? All these things are reasonable things to write as the range. Okay. So the range is more ambiguous than image. Okay. Just to make this distinction. So if I wrote, for example, f of x equals x over x plus 1, and let's say that f is going from positive reals to the reals. What's the image of this set, of this function? Can anyone tell me anything about the image of this function? What kind of outputs can I get out of this function? Do I get the whole real line? Can anyone tell me just anything about it? Mariah, I think you were first.
X cannot equal -1.
You can't get -1, so the image -1 is not in the image. Can anyone tell me more about it? What about other negative numbers? Can I get other negative numbers? Can I? No, I can't, right? Because I'm taking, my domain notice is only non-negative numbers, right? And so I'm putting in non-negative numbers into this guy. I get a non-negative number over a non-negative number. They're all going to be, so I know that, even better, there are no negative numbers in the image. Right. Can anyone say a bit more about it? Anything more? Could I get, say, 2? Could I get 10 in this? Could I get the number 10 as an output? Kimaya?
All the outputs are going to be less than 1.
Yeah, all the outputs are going to be strictly less than 1, right? Because I'm taking a positive number, a non-negative number, and dividing by something bigger, right? I'm dividing by something bigger, so all these guys are less than 1. How low can I go? Can I go all the way down to 0? I can get 0, right? If I put in 0, 0 is part of the domain. So I mean, we're starting to believe that maybe the image of f is 0, 1, 0, 1. Right? Maybe we're believing that. Okay. So it looks like that ought to be true. Right? Let's check it. Let's check it. Suppose y is in 0, 1. What is there an x? Is there an x so that f of x equals y? Right? We're starting to believe that it is all of 0, 1, but can we really get every number in 0, 1? Let's figure it out. Let's choose an arbitrary number y that sits inside 0, 1. It could be a half. It could be anything. It's the number y. Okay. Okay. So is there an x that that when you feed it to this function, the function hands you back the y that you were looking for? So you'd say, well, look, we want x so that x over x plus 1 equals y. Right? Right. We're wondering, is there an x so that f of x equals y? Right? So that x over x plus 1 equals y. Right? And how do you solve for such an x? I'll let you take half a minute and solve for x. What is x? What x will do? Okay, turn to somebody next to you and say what you got. What's the question? You have a question? You have a question?
Well,
Yeah. Go ahead and ask. Ask it. Be brave. I spent my entire college education not asking any questions and being too shy to ask questions. Like if I had a question in class, I start to raise my hand, and then my heart would start pounding. Like throughout college, I'd say, and so I never dared to ask any questions. This is sort of a mistake, of course. You want to ask questions. Or if I had a question that occurred to me outside of class, then I'd try to go ask the professor. And so I'd walk over across campus at office hours to the tower where all the math professors lived. You go into the tower, and then I would sit outside the professor's door, thinking about my question because I didn't want to seem stupid to the professor. Because these were like world-class geniuses in the tower, right? So you don't want to seem stupid. And then I figure out the question, and then go back to the library. So, anyway, so yeah. I encourage you to ask questions, but I understand that it might be difficult. Okay. Okay. So how do you do this? How do you solve for x? Well, somebody would like to say, Victor, you had your hand up. Yeah.
So you multiply x plus 1 to the other side.
Sure.
Then you
Distribute.
distribute. Take yx to the other side.
Okay.
Factor out dx.
So x, 1 minus y is y. And so x is going to be y over 1 minus y. Is that right? Did I make a mistake? No, that's right. That's right. Yeah. So that x will do it for you, right? When you feed that x into the machine, it will return y. We can check that if you'd like. So let's check. If we feed that x into the machine, do we get y? Well, f of x is going to be f of y over 1 minus y, right? That's to say, y over 1 minus y over that plus 1. Right? So y over 1 minus y plus 1. Right? F of x is going to be x over x plus 1. Right? X over x plus 1. And let's multiply top and bottom by 1 minus y to make this cleaner. Let's multiply, just to make it cleaner, let's multiply by a cleverly chosen 1. Right? It's okay to multiply by 1, just as it's okay to add 0. So let's multiply by 1, where 1 is 1 minus 1.
Sorry, where'd you get that from? The last part?
This thing here?
Yeah, no.
So this is, we're putting in this into our function. Right? What's our function? Our function says,
Okay.
whatever you give me, I'm going to give you back that thing over that thing plus 1. So it's going to be this thing over this thing plus 1.
Okay.
Okay. And let's see what that is. Well, that's going to be y, right? Y over y plus 1 minus y. Right? Which is 1. And so we do get y out of it. Go ahead.
Can you do that last time?
Sure. Right. So it came here. I have the thing over the thing plus 1. I multiply by 1 minus y on top and bottom because you see I've got this 1 over 1 minus y here. So these guys will cancel, and I'll get y at the top. Here I multiply this thing by 1 minus y. I get y. I multiply this thing by 1 minus y. I get 1 minus y. Right? You distribute in this thing, right? So a plus b times c is ac plus bc. So if this is my c, I'm going to multiply a by c. I'm going to multiply b by c. Right? So when I multiply a by c, I get y. When I multiply this guy by this, I get 1 minus y. Okay? And so I get c under y. Okay. So that's right. Like this is if we can get any y. Or we can get any number in 0, 1. So yes, was this the image? Yes. Okay. Any questions? Anyway, the main thing is that we're just saying that this function has this image. And I've thrown in this thing as sort of a foreshadowing of something that will happen later. Yeah.
I don't understand how we factored in what we had as the image into our check.
Could you say one more time?
Yeah, so like how does that prove that the image is 0 to 1?
Is 0, 1. Okay. So we suspected that the image was this set, right? And we thought, well, it seems like we're pretty sure that, it seems like this is going to be it. So is it really true that we can get any number in 0, 1 out of this function? Let's find out if we can. Choose any number in 0, 1. Here, choose any number in 0, 1, call it y. Okay. We work it out, and we see that if we feed in this thing to our function, out pops y. Okay, so now what we're saying is that you know, if somebody says, I don't believe you that the whole thing is 0, 1, can you get a quarter out of your function? And you say, sure I can. All I need to do is feed in quarter over 3/4. All I need to do is feed in 1/3 into my machine, and then out will pop your number. And it says, oh, okay, what about 1/5? And you say, well, to get 1/5, all I need to feed in is 1/5 over 1 minus 1/5, and then out will pop your number. So we've created what we're saying is that whatever number somebody wants you to create, there's an input. Whatever number somebody wants as an output, there's an input that gives that output.
Okay.
Okay. Can you get this output? Yeah, sure. I'm just if I feed in this thing, out comes your output. Okay, so I can get every number between 0, 1. So that actually is our image, as we suspected. Kimai.
How would it disprove that we can get something out of that set? Like what if you put in 20, you would still get a number?
Say it again?
What if you put in something that wasn't between 0 and 1? What if you put in 10 into like that?
That's okay. That's okay. This is what we're talking about is the numbers that come out of it, right? What we're saying is that the numbers that come out are exactly these numbers, are exactly this set from 0 to 1.
Okay. So what if someone was like, can you prove that you can't get 10 out of that?
We actually already did that, or maybe I think you did that when you noticed that this number can't be bigger than 1.
Oh.
Yeah. That was you, right? Yeah. So we already know that. We already know that the image is between 0 and 1, and now we're showing that it actually is everything between 0 and 1. Yeah, Dean.
So the function we got y is 1, 1 minus y.
Yeah.
That is the domain is basically the image of this function. Good.
Yes, that's true. Yes, that's right. Yeah. So this is actually, I didn't want to say it, but this is actually the inverse function. Yeah, this is actually the inverse function. It does the inverse. Okay, but let's go on. Let's go on. Okay. Unless there are any questions. Okay. So other notation. There are things called piecewise-defined functions. If I write g of x equals 1, for example, if I write g of x is 1 for x bigger than 0, and 0 for x equals 0, and -1 for x less than 0, then I think you know what I mean, right? Right. It says that if you feed in, if your x's are negative, it's going to give you back a -1. If you feed in the 0, it's going to give you a 0. If you feed in a positive number, this function will give you back a 1. Okay, so is everyone familiar with this sort of notation? I guess I already used it when we talked about the absolute value. Remember, the absolute value was x if x was positive, and was negative x if x was negative. Right. This was also a piecewise-defined function. Okay. Just to recall the notation. Right. So visualization of functions. Right. For functions f going from R to R, one has a useful visualization of it. We call the graph the set of xy in the plane such that y equals f of x is called the graph of f. So it's all points, right? You have some function, right? You have some function. Really, the function goes from R to R. This function goes from R to R. To some x, it associates some value f of x. Right? You know, for example, the square root function, say. If we think about f, the square root function, then you could think of it as a bunch of arrows going from the real line to the real line. Right? It takes 0 to 0. Right? It takes 1 to 1. Right? It takes 1 to 1. It takes 4 to 2. Right? It takes 9 to 3. It takes all these things in between. Right? So that's what the square root function does, right? It's this association. But that's sort of hard to visualize. And so instead, what you do is you take you take this line and you lay it flat, and you take this line and put it vertically, right? And you take the plane. And you say, okay, instead, what I'm going to do is for one, I'm going to put this point here at the so that the y value is f of the x value, right? So this is 1, 1 because f of 1 is 1. Right? Of course, you've got 4, 2, right? 4, 2 because 2 is the square root of 4, right? So here 1 is the square root of 1, 2 is the square root of 4. Right? 9, 3 is also on the graph because 3 is the square root of 9. Right? So it's all points. Xy such that y is f of x. Right? Y is the square root of x. Right? So if we fill it all in, it's this thing here. Right? This is the graph of the square root function. Right. Right. Just now we had this function g, which was 1, x was positive, 0, x is 0, and negative 1, x is negative. Right. What does the graph look like, Sarah?
Sorry, I
Yeah.
don't understand the top part.
Yeah. So I mean, this is really what the square root function does, right? It takes in a real number and then returns to you a real number, right? This is the domain and this is the range,
Okay.
right? So you could think of it as a bunch of arrows, right? As a bunch of arrows, right? When you give it a 0, it returns you a 0. When you give it 1, it returns you 1, right? When you give it a 4, it returns you a 2, right? Et cetera, et cetera. And there's stuff that goes on in between as well, right?
Mm-hmm.
Right? So really the square root function is all these, you could think of it as being summarized by this picture of a bunch of arrows. But that's sort of hard to understand. And so this is the more easier visualization, right? That's what a graph does for you.
Okay.
Same thing here, right? What kind of points are going to be on the graph? Well, for example, 0, 0 is going to be on the graph. because f of 0 is 0, right? 0 is 0. I'm sorry, is g of 0, right? Et cetera, right? So like if you have any positive value, you're gonna get a height of 1, right? So it's gonna look like this. Right? Put in any negative value, and you get -1. Right? So this is the graph of this function, which is actually has a name, the signum function. Signum or sign, right? It tells you the sign of your number. Right? Is it plus or is it minus or is it 0? Yes.
So does the line sort of represent the range then?
So what's the range in this picture? What's the range in this picture? The domain. What's the range in this picture? So
That was all.
yeah, I mean, so really, like I said, this thing is the domain and this thing is the range. This thing is the domain down here, right? This thing is the domain and this thing is the range, right? But if somebody gave you a graph like this and said, what are possible inputs, right? What's the domain? What are all the possible inputs? Well, you would say, well, what kind of x values does this function take? Say, well, you can take anything for x, right? Anything for x will do, right? What about the image of this function? The image of this function, the collection of outputs.
Anything that's
What kind of things does the function return to you, Mia?
It's length.
Length, so-
-1 to 1.
-1 to 1. Does it give you everything between -1 to 1?
-1 and 0.
-1, 0, and 1. That would be the image of this thing. And so you see how you get the image is you squash the graph. You take the shadow of the graph onto this line here, right? So over here, right, what's the image? You shine a light from over there, and you'd see, oh, I'm going to get positive numbers, right? What I get are just all positive numbers, all non-negative numbers. That would be the image of the square root function. And the domain, you see, would be all the non-negative numbers. And you have some light way up high, and see what shadow you get on the plane here. But what you call this is a projection. You project the graph down onto the axis. Somebody, you might.
So would the range be all of
Yeah, again, the range is sort of an imprecise thing. We could say range is all real numbers. We could say range is the set -1, 0, 1. We could say, we could say a lot of things. Yeah.
How do you write the image for this one? Like, how do you?
You just say the image of t is -1, 0, 1. The set of these 3 points.
Oh, it's the set.
Yeah, Stefan.
So you said with the range you could say literally anything?
Well, not literally anything. Like you couldn't say the collection of oranges or something.
But like any collection of numbers?
Well, it would have to contain containing these three numbers.
Oh, containing those three.
Yeah. So, for example, I could say the range is the integers, because certainly the outputs are integers.
Yeah.
I could say the range is the rational numbers, because the outputs are rational numbers. Right? But the most precise thing you could say is that the image is these 3 points, -1, 0, 1.
So anything that includes all three, but does it have to include all three?
Yeah.
Okay.
Otherwise, it's not.
Okay.
Yes, Sarah.
So is the range just like a less specific
Yes.
version?
Yeah. It's just a less. It's sort of, if you don't want to figure out exactly what the image is, you say, well, the range is the real numbers. Right? Often you don't need to know exactly what the image is. Okay. Okay. So one can do this in general. Mark one can do this in general. For example, for f going from R2 to R, f going from R to R2. So one can, when I say do this, what I mean is one can create graphs. You don't have to be going from the real numbers to real numbers. You can be going from any set to any other set. It still makes sense to talk about a graph, even if you cannot see the graph. So this is a graph. This would be some sort of four-dimensional graph. We wouldn't be able to see it, but we can still talk about it. We can still define it, right? It's still going to be points in R4 where the second point is the output of the function of the first point.
What is that two?
The plane. So R2, when we write R, we mean the y. When we write R2, we mean the plane. When we write R3, we mean space, etc., etc. So here I'm saying any point on the plane where the y coordinate is f of the x coordinate. Okay. And you all know this. Does every set in R2 arise as the graph of a function? And the answer is, of course, no, right? Because, for example, if you had something like this, then what that would mean would be that, let's say this is x, this height is y1, and this height is y2. If the graph looked like this, what would that mean? Just by the definition of the graph, what?
It's not a function.
It's not a function. Why isn't it a function? What does this mean? If I have this point on the graph, x, y2, well, that means that y2 is f of x, right? Here I've got another point on the graph, x, y1. That means that y1 is f of x, right? So there, f of x is y1, f of x is y2, right? That's not a function for us, right? Because our functions assign only one value to a single input, right? So it's not a function, not the graph of our function. Yeah, Victor.
Could you say that it is a function, but just of y? Could you say that it's a function of y?
Oh yes, you could. Yeah, but yeah, don't think about that. Right? Yeah, this graph would be the graph of a. But don't just forget about it. Although it's true. Okay. Yeah. So this is the the vertical line test that you've not seen before. Vertical line test. As long as the set passes the vertical line test, one can use it say like this. One can use it to define some function, a function. Okay. So last thing. I want to introduce is the simplest sort of function. And maybe I should have done this first, but I'm going to do it now. Simplest kinds of functions are for us, the simplest sorts of functions will be sequences. Okay, so these are functions that associate to numbers. So 1, 2, 3. The domain is going to be the natural numbers. Okay. A will go from the natural numbers to R. So to every natural number, it's going to give some output. Right? To 1, right? There'll be an A of 1, there'll be an A of 2, there'll be an A of 3, there'll be an A of 4, but there's nothing in between. There's no A of 1.5. There's only A of the natural numbers. Okay. So for example, if I write A of n, so A going from n to r, being where A of n is 2n, right? Then A of 1 is 2, A of 2 is 4, A of 3 is 6, A of 4 is 8, etc., etc. Right? A of 1 is 1, A of 2 is 2, A of 3 is 6, A of 4 is 8, etc., etc. And so this gives a sequence, right? This function's output gives you a sequence, and that's why we call these things sequences, right? So it gives you a sequence 1, 2, 1, whoops, 1, what am I doing? 2, 4, sorry, 2, 4, 6, 8. Okay, it gives you a sequence, namely the sequence of even numbers, right? Has anyone not seen sequences? Not ever seen sequences before? One thing that I think might show up in the homework is something called, I'm sorry to keep you a little bit over, but let me just make sure that I get this down. There's something called a recursively-defined sequence. And that's where you don't introduce it as a function, but you define your elements in terms of previous elements. Okay, you define, an element of the sequence as, something having to do with the previous element. So, for example, you could say A of 1 is 1, and AN is always going to be 2 of AN minus 1 for n bigger than or equal to 2. Okay. So what that would mean is that the first one is 1, and then after that, everybody is twice the one before him. So A2 is going to be twice A1, right? A2 is going to be twice A1. A3 is going to be twice A2. A4 is going to be twice A3, etc., etc. So there's a recursion, right? The nth guy is twice the n minus 1th guy, right? And so my sequence would be what? 1, 2, 4, 8, because it's going to be twice the previous guy. Each one is twice the previous one, right? So 16.2, okay, powers of 2, right? Or you've undoubtedly seen the Fibonacci sequence, right? Fibonacci sequence. Maybe, I don't know, maybe you haven't, maybe you haven't. A1 is 1, A2 is 1, and for n bigger than 2, A sub n is the sum of the two previous. The two predecessors of that one. So A1 is 1, A2 is 1, A3 is going to be the sum of the two previous guys. A3 is going to be the sum of A2 and A1, that's 2. Right? A4 is going to be the sum of the two previous guys. This guy's going to be the sum of the two previous guys, the sum of the two previous guys, the sum of the two previous guys, etc., etc. And you get this is what's called a recursively defined sequence. This sequence, as you may or may not know, occurs in nature. Apparently, they say that you can find them on find Fibonacci numbers on pineapples and stuff. Anyway. Okay, that's it for today.